Good morning. I'm Zhang, and this is my partner, Julia Lin. We are from the high availability architecture team of Alibaba, and our topic is about capacity planning. As we know, Alibaba has very rich business types, and to each business type, we have different systems to support, which are distributed on different machines. With our business growing fast, especially in the big promotion events like Double 11, we had a headache problem. That is, we didn't know how many machines we need to prepare for each business system. If we do not prepare enough machines, applications will not work. While if we prepare too many machines, it will be a waste of money. So there is actually a research topic named capacity planning in Alibaba. To make each business system clearly knows when it's necessary to add more machines, when it's safe to remove machines. Besides the dynamic adjustment, the most important target is to have an accurate estimation about the optimized machines needed for each system to ensure the site availability and also do cost saving. Capacity planning is divided into 4 stages. The stage 1 is workflow estimation, to analyze historic data and estimate the access volume at certain time point in the future. This is more about model and accuracy problems and is not the main focus of this presentation. The stage 2 is capacity estimation, to make a rough estimation about the machines needed for each system. In stage 1, we already know the access volume of each system. For the purpose of capacity planning, we should also know the service ability of each machine to each system. We get this value by doing single machine stress test. What makes it special is that such stress test is made in production environment directly at Alibaba, because we must make sure that the environment and the requests are real enough. Otherwise, the test result will have big gap between with real data and affect future conclusions. So there are mainly 4 measures for the single machine stress test. That is simulation, replication, redirect, and load balance. We will explain them one by one. The simulation method is easy to implement. We can just send simulative requests to a single server to test its service ability. This is a common idea, and there are quite some open source or business tools, such as Apache AB, Webbench, HPLoad, JMeter, and Roll-Run, and so on. Simulation is simple enough, but has an inborn defect. The simulative requests are not exactly the same as the real requests, so the test result may not be accurate. Another defect is to deal with write requests. You know, write requests will infect backend stores such as database, cache, and so on. We need to isolate the infection otherwise it will bring dirty data. Simulation for single-server stress test is usually used in the case of new systems. Because of the unreal problem detected in simulation method, one improvement method is republication. Requests are recorded from online machines and then sent to another test machine. Replication is more accurate compared to simulation because the requests are all real. However, replication also has to deal with the infection of write requests. Besides of that, we need to tackle the response about the replication requests, so the test machine needs to be separated and cannot provide normal service. Replication can copy several times of requests, so overall speaking, it is usually used in the case of systems which has not many requests. In the previous two methods, we both get problems about write requests in production environment and do a lot of work like isolation. Is there any simple way to finish single machine stress test? Yes, we do have simple ways. One method we used is called redirect. As I introduced at the very beginning, Alibaba systems are all distributed and means multiple machines handle the incoming requests. Then, if we can redirect requests to the test machine from other machines, of course, the test machine will have heavy load, and that is what we want to do. So it's easy to understand. Redirection method can have very accurate results and needn't to deal with write requests. Also, it's easy to implement. Just a redirect switch is okay. This method is widely used in Alibaba's web systems because the web systems always have a reverse proxy module. While a small problem for redirection test is that the requests should be large enough to exceed single machine's ability. Otherwise, even when we redirect all requests to one machine, we still couldn't test its serviceability. So we need more requests. Load balance is similar to redirect. As you can see from the picture, the middle machine gets more requests than other ones, while the difference is to use a load balance device in the middle to dynamically adjust workload. We do all these things on the single machine stress test platform. A test will be triggered automatically or manually. We always start a single machine test after a new release. We must be very cautious about this because we are doing stress tests in production environment and mustn't affect the user experience. So, monitor module of the platform is very important. Stress test will stop immediately when the system indicator exceeds the threshold. After every stress test, we will generate a test report. Now we have the estimated request volume from stage 1, and we have the tested single machine capacity from stage 2. Then it is very easy to calculate how many machines we needed. Just like this formula. Of course, we also need some buffer to prevent accidents. After stage 2, is it good enough? Of course not. We learned a lot of practical experience in the Double 11. Although we made lots of estimation and preparation, when Double 11 festival started, we found the machine performance was worse than we expected. And many systems were in high risk. So we need to do something more. The stage 3 is for fine-tune. We use full chain stress test to simulate end-user behavior in big promotion events, so we can verify the capacity estimation made in stage 2, and also fine-tune the machine numbers to reach optimized value. What we had done was single machine test, like a single geo. The more accurate the test, the better estimation we can make. But as talked, this is still an estimation, and will always have gap with real situation. So when all these geos are connected together, geos are associated with each other. Small gaps will be amplified so quickly and heavily. We don't know what will happen in the real situation. So this tells us it's not enough to only test a single machine, but we need to test the complete business as a whole. Then, no matter how large the gap will be accumulated to, we can always get the result in this complete test, and they'll take action to improve. But how we can test the complete business like Double 11? As an example, in China, students need to have final examination each semester. While before that, teachers will give students some simulation tests right before the final examination. To us, the Double 11 is just the final examination once a year. If we can make a performance simulation for Double 11 before the real day, then the system can be tested completely. Then we can verify whether the capacity is we estimated before, and whether there is any part needs to be improved. Although it is not hard to think this ideal, but it is not easy to simulate Double 11. Because in that day, we have hundreds of millions of people on Alibaba to select and purchase millions of different products. The real scenario is very, very complicated, and there are mainly 3 challenges. First challenge, the incoming request volume is very large. System will receive over 10 million requests per second at 0 o'clock of Double 11. The second challenge, the simulation scenario should be close to users' behavior in Double 11. One user behavior is simple, but but 100 million user behavior is complicated. The third challenge, as all the machines are in production environment, we need to finish such simulation in production environment as well. So how to make sure the test data will not affect real business is another challenge. With the 3 points mentioned, we developed a new stress test platform called full-chain test platform, which can meet all these requirements. How to create more than 10 million requests per second? We create a new flow control platform, which is composed of a control node and thousands of work nodes. On each work node, we deploy the stress test engine we developed. The stress test engine needs to have very good performance, otherwise we will need too many workloads. In addition, it should support all protocols for Alibaba business. The stress test engine is deployed on CDN nodes throughout the country, just like users from different places. With all the thousands of work nodes work together, we can control the stress test cluster very easily, just like control a single machine. We can use it to send whatever amount of requests we need to test. Then the second challenge, user behavior. We all know W11 is a very complicated business faced with lots of scenarios, and we hoped to cover all of them and put them in this full-chain stress test. So we did these things to make it happen. First of all, to dump enough data from online database, including buyers, sellers, products, discounts, and so on. Then, make necessary filter and remove the sensitive fields like telephone numbers of users. We store this data as the basic data. Based on this basic data, use the estimation algorithm to generate the business model of W11. The business model contains hundreds of factors. For example, buyer number, buyer class, seller number, seller class, product number, and product class, and so on. Once the business model is ready, finally we can then create corresponding test requests and then upload the requests to the test engine. So this ensures our test data is very similar to users' real behavior, and the test result is then convincible. Now, the last challenge, data pollution problem. Do you remember when we were discussing single machine test? The simulation method is not good just because the right requests will generate dirty data to affect business. But since this full-chain stress test happens before the real activity, so it must be a kind of simulation and will have dirty data. Data isolation is needed. However, in distributed systems, isolation is not simple. All the requests in full-chain stress test are marked with a special flag. This flag will be passed through different systems. Requests once added this flag will not be removed. So every middleware should support this flag in its protocol, such as RPC framework, message queue, cache, storage, and so on. Whenever this is a write operation, we add a check and we'll write the data to a special area which is isolated. This area is called shader area. We try to do all the things in the middleware so that business systems needn't to be modified. A complete full-chain stress test contains 3 steps. Step 1 is data preparation, including basic data, business modules, and user requests. Step 2 is stress test preparation. We should warm up systems, upload data, and check whether everything is okay by pre-run a small traffic flow. Step 3 is stress test execution. Adjust machine counts among different systems at the same time, then generate a test report. Full-chain stress test was first used in 2013. Before Double 11 that year, we used it to find more than 700 system problems and immediately get resources to fix them. Then the Double 11 was quite smooth, and the site availability was much better than before. In the next 3 years, we continued to use this test platform and found hundreds of problems again, because every year there will be lots of new components added in and could generate new problems either by itself or by the collaboration with existing components. If we didn't find and fix these problems, they could burst in our Double 11 feast and cause unexpected results. With the success in Double 11, now the full-chain stress test is widely used in all big promotion events, like March 8 Festival, September 9 Festival, and so on. It quickly became one of the most important indispensable step for us. Actually, in each big promotion event, we will take several rounds of full-chain stress test to make complete simulation of the whole system and reveal any hidden problems. We are proud to see this is our nuclear weapon in site availability guarantee. The stage 4 of capacity planning is about traffic flow control. And my partner, Julia Lin, will introduce the contents of this section.
Good morning. I'm Julia from the same team. I'm Julia from the same team as the Zhang. So here we come to the last part about the flow control. Before that, we are all discussing about the capacity planning, which is based on the first estimation in the first step. Such estimation comes from a complex model with the historical data and the algorithm as an input. however, no matter how strong this model can be, it's still estimation. So we still have the potential risk that the real coming volume is much larger than what we have prepared. And the worst part is that the buffer we have prepared may be too large for the gap. So here, so the recent sample is our last Double 11. After carefully calculation, we have prepared enough volume for 160,000 requests per second for the peak time. But actually, that date, the peak volume has reached 180,000 per second. You may have seen that this is just for peak time, and the additional 20,000 requests will be consumed very soon. But I can tell you that it's not true. Actually, it did happen several times. Imagine that a machine is overloaded, then the response time of his request will become much slower, and this will delay the normal process. The delay will cause the bad user experience, and the user may retry to submit their request. This makes the incoming request even larger. And as the new common requests is being accumulated, the system performance will go down steadily and result in the no response in the worst scenario. That's just for one single machine. And as this machine has no response, the network balance will redirect the request to the other machine. And this adds more tasks to the other machine. And the other machine will soon go into the same, will soon run into the same problem as the first non-responsive machine. And in a short time, more and more machines will go down, and the cluster will no longer provide service. The so-called echelon breakdown will occur. When this chain react starts, it's harder to stop. So we need a mechanism to monitor the system status, to control the incoming request volume, to prevent such things from happening. Flow control is not only used in peak time, it can also be used in many other scenarios. For example, there is an application which downstream the application is in problem with long response. Then this will generate amplified effect. The response time of the full business chain will be increased heavily and maybe no function. Which means that we also need to do flow control based on response time. The other question that I want to discuss here is the actions to be taken after the flow control decision is made. For some applications, it's very simple that we can simply discuss this request. For some applications, we need to we can queue this additional request to a temporary queue and let the application consume them later after the peak time. And sometimes we need to demote this system directly. Finally, we need a flexible framework which has 3 dimensions. One is the running status. The other is the flow control methods. Means when we need to do the flow control, we can demote it or even add it to the blacklist. And And also, we can also do the flow control according to its core relationship. This picture is the general principle for the flow control. First, we need to add a process to the entered methods. With this process, we can use that 3 slots to monitor the running status, to check down all the calling relationships. And download 3 blocks. Here, we use these blocks to receive the predefined rules and use the running status collected by the upper 3 blocks. Then we can receive flow rules and monitor the application status and do workflow immediately. So the previous 3 parts, we are talking about how to do flow control when the system is abnormal. Imagine what happens if the flow control is triggered. The system is safe after flow control is triggered, but it's running in a restricted mode. So let's use the previous example. The flow control is triggered when the downstream application is in problem with the longer response, and results the system is in high system load. After a while, the downstream application is recovered, and the response time has been reduced heavily, or has been reduced obviously. But however, the system load is still high because the incoming request has been accumulated for a while. This means that if we use the system load as the trigger to flow control, then even though the problem has been fixed, because the system load is still high, and the flow control is still here, so the request that can pass through the system can only be added slowly. This results in the slow recovery. We need to do something to improve this. Imagine a tube. As you may already notice that in the response time compared to the system load, the response time is more accurate to reflect the system status. So maybe you can use the response time as a factor in the flow control. Imagine that we have a tube full of water. It takes the water RT time to go through this tube without any waiting. And here comes the water with volume L. Then how large our entry size could be? Then this water with volume L can pass the tube without any waiting. This formula can be easily reduced that when the entry size equals to volume plus the response time, the water can pass the tube without waiting. Now we have the formula. Let's map this formula to our real system. When the system is in the high load, that means the tube is full with water. And the response time is the time the water to go through this tube. And because load, actually the real meaning load is how many tasks can be wasted in the system. So, and it's in the direct proportion with the coming request with our tolerant capacity. So we can just simply map volume to load as a constant multiplied load. The constants is decided by different application. So finally, we get a formula to our system is that the request we allowed coming into the system equals a constant multiplied load and multiplied response time. With these three factors, if we keep these three factors balanced, we can keep the load in a stable status without growing. This is the result of our new method. The first one is the relation becoming the incoming request. The blue line is the incoming request. The orange line is the response time, and the brown one is the load. As we can see, when the system has hit a very high load, according to this formula, we adjust the incoming request according to the formula. The high load can be reduced steadily, and finally you will keep to a stable level. And the second picture is about the relation of the incoming request and the response time. After you can at the rectangle part, you can see when the system's response time has been recovered, it has been reduced. When it has been reduced, the allowed incoming has recovered very quickly. So that's all part of our workflow flow control. The flow control we have talked about the traffic flow control. We have talked about the principle of the flow control and the framework of the flow control, and when to take action and when to recover them. With these four parts together, the business model estimation with the capacity estimation, with the full chain stress test to verify whether our capacity planning is correct and to fine-tuning them. And when in the real production mode, we will use traffic flow control to make sure that the system work as our estimation. Thank you.